So today we are looking for another analysis which is also related to airfoil. Okay, so this time it must be much more technical. Okay, so in the previous case we already analyzed airfoil, so we do that analysis for an external flow analysis. So today also we do the same thing with a much more depth in the previous case. Okay, so this topic comes under the chapter of transonic flow, externally compressible. Okay, so here we use the transonic condition for airfoil structure. So they give all the factors like match number, and then how velocity and alpha angle. So we have to convert this alpha angle for sine and cos values, so which will be covered in our session today. So basically we have that mesh file, so everything is by default. So that file is actually in the format of .msh. So I already said in our last session. So we don't yet design this airfoil and try to create a boundary and meshing. So everything will be already created. Okay, so we just imported that MSHI file and assign the values. Okay, and I hope you all know about what is transonic and hypersonic and supersonic. And if you have still any doubts about this, transonic means the air which is headed on this airfoil is nearly equal to that velocity of the sound. Okay, so and also you have the cases of supersonic and subsonic also. Okay, and when you are going for a supersonic, so that match number will excite the value of 5, so 5 and above the 5. For this case it may be around 1.82, I mean 0.8 to 1.2. So in our case we choose it as a 0.8. Okay, so let's get into the Ansys workbench. So first I will open the workbench and drag and drop the Fluent flow. So there is a lot of stuffs. I will try my best to explain whatever it is necessary for our case. It is mostly related to the aerospace engineering, so that we include lot of factors. So we thoroughly follow that Ansys tutorial book, so which is actually downloaded from the Ansys website. So I will also share that PDF at the end of the session. You can also follow that particular tutorials. Okay, so just right click on the mesh. So if you want to import that MSH file, so right click and you'll have an option to import the mesh file. So just click over here. So you will notice that there is a file that is airfoil4.msh, so which includes the mesh data and the boundary condition. So boundary condition in terms of that inlet and then outlet and then region, that is air region. Okay, so in this analysis the Fluent is air. So now the imported mesh data is get loaded. So the geometry and then mesh option is turned into like a imported mesh data. So you can't edit this data. So you can, but you need to import a separate external model file and try to open the geometry and change the mesh configuration. But for now I don't want to change the mesh configuration. I just directly get into the Fluent environment. So just double tap on the setup. So this probable actually, okay, so we'll use that double precision method. So once it is get selected and click on start, Fluent is get started. Okay, so this is our airfoil structure, and this is the predefined mesh. So they use a washer structure method. and also they use the phase meshing method to create a proper quad mesh around this texture. So there is not a single single triangular element over here. So the mesh is very good. So still you can check this condition. So click on check, and everything is fine. So if you are facing any issues, you have to make sure and change the necessary things in the model. Okay, so again this is a compressed flow, so we'll use that pressure based model, and I don't want to change anything from here itself, and it's a steady state condition, not a transient one. And directly we will move on to the model, and in this model it involves the temperature. So that the first thing I need to change is turn on the energy equation, double tap on the energy. So just click on energy equation and say okay. Now the energy equation gets turned on. So this will be reflected in the cell zone condition when we assign that boundary conditions, like that velocity of the air, everything. So in that a temperature tab will be enabled to assign the temperature of the air. Okay, so once it is completed, the velocity, that energy equation, and we are going to change the viscosity condition. So we have so many viscous conditions. So that is inviscid. So you already know that. So this is for frictionless flow, that is which is very there is no viscous at all. So it's like a liquid water. But this is laminar flow, and all the conditions we have is for a turbulent flow. Okay, so in this condition, so usually for a turbulent condition we use k epsilon or k omega, so which is suitable for shear free and no wall boundary conditions, but this time we use Spartlet. So it's a single equation which is more suitable for the aerospace application, and there is no wall bounding flow in this condition, and it's very good for convergence also. So we'll get a convergence as soon as possible. Okay, so with the 1000 iterations or 1500 iterations, it's maybe it depends upon the mesh condition. We'll choose it, and if you don't get convergence result, we'll try to change that k epsilon or k omega itself. So that so recording this session, you'll get this recording also. So once it is set down, I'll change the values so according to your book. So we'll have that option to change the velocity. What is this? So have you ever heard this term? Velocity is okay. Vorticity. So usually, normally in a turbulent flow or a laminar flow, in laminar flow the liquid flows in this manner. Okay. So I'll just type that. So laminar flow versus turbulent flow. Maybe images. Yep. So this is a best example. So this is what a laminar flow means: a smooth flow over this region, and turbulent flow. So this is what turbulent flow. So this value, which denotes, here you have this 2/6. It shows that pseudo vector. So vector, you know that the direction definition factor. So pseudo means like a spinning moment. Okay, so the liquid or air that may be flows in a spinning manner like this. So if you want to define this factor, you can use this. So, and I also included the strain. So I'll choose strain velocity's basis. So once it is selected, so I don't want to change any other factors. I just leave as it is and say click on OK. Now the viscous condition is get assigned. Once it is assigned, and I will move on to the material creation part. So in the material, so by default we have the material that is air, right? Okay, so now the material conditions is get opened. So since you enabled that energy equation, you get that additional condition, options that are CP, specific heat, and thermal conductivity is option. So if you want to change those values, you can, but I will leave it as it is. Okay, so one thing I want to change here is that is viscous condition, viscosity. So right now the viscosity is set to constant. Again, you have a various method. I'll choose Sutherland. Okay, so this Sutherland method, which is actually invented in 1892 or 93 by William Sutherland. So basically it relates the dynamic viscosity and then absolute temperature, that is nu and T factor. So to create a smooth wall transition. So if you have this foil, right? So the air is hit on the wall. So the viscosity, the smooth transition around the wall, it actually captures much more better. If you have time, just search for that Y plus factor. So we will also find the wall Y plus graph at the end of the session. So this wall Y plus factor and that Sutherland law will have some connections to find a smooth flow around the edges. For better result, just enable this and make sure it is in the 3 coefficient methods. So I don't want to change anything, so I will leave it as it is. So once it is, get selected and click on OK. So that click create and change and say close. So the next thing is we'll move on to the boundary condition. Okay. So in boundary condition, you know that inlet and then internal and wall condition. So just double tap on the boundary condition. I'll choose pressure field, that is the overall region, and say click on edit. So here you will have the option to change the match number. So based upon our problem statement, that match number is 0.8. Okay. So match number is the ratio of U. It's not nu, it's U, that is velocity, and C, and speed of the sound. It defines the flow as whether it is supersonic or subsonic, and what is that, transonic. So we determine by this factor, so whether it should be lies on F8212, we say it as a transonic. So over 5, we say it as a supersonic one. So other than that, I'll change the X component flow direction and Y component flow direction, which is actually comes from this factor, that is alpha 4 degree. We have that alpha 4 degree over here. So how can I measure that? So we need to resolve this component by using trigonometric function, that is sine alpha and cos alpha values for X sine theta and for Y cos theta. So you can also search for that value in Google. So that is sine 4 degree theta sine 4. Okay, 1 second. So that is, we have this value. I just copy this value. So this is actually for y component. So I'll just paste that value. And similarly, we need to calculate for the cos. So cos 4. Lag irka. So is everyone facing this issue? Is there any okay, 1 second, I will check my internet connection.
Yes sir,
So Manoj, you are facing any issue? Still you are facing that issue? Okay. Okay. No issue. You will get this recording. That will be much clear. Okay. Fine. So I'll use the standard values, that is 0.9975. Okay. So once it is set it down, the temperature will be 300. So it's set it and say click on apply. So then click on close. The pressure far field 1 is screen. Okay, so still you are facing that issue. Bharat Kumar.
அது நான் என்னோட பிரச்சனை நினைச்சிட்டு இருந்தேன்.
ஓகே,
உங்களுக்கு தான் பிரச்சனையா?
டேய் ஒழுங்கா கேக்குதா இல்லையா?
அது ஒரு மாதிரி நீங்க உங்க வாய்ஸ் வருது சார், பட்
ஓகே
கேக்குது சார், பட் ஆனா அது வீடியோட சிங்க் ஆக மாட்டேங்குது.
வீடியோவோட சிங்க் ஆக மாட்டேங்குதா? என்னடா சொல்றீங்க?
வீடியோ கொஞ்சம் ஸ்லோவா நம்பர் சொல்றீங்கன்னு வச்சுக்கோங்க. இந்த டைம்ல அது
ஓகே நான் லெஃப்ட் ஆயிட்டு திருப்பி ஜாயின் பண்றேன்.
அது நீங்க சொல்லி முடிச்சதுக்கு அப்புறம் தான் ஸ்கிரீன்ல வருது.
ஓகே
லெஃப்ட்
ஆயிட்டு என்னடா டீம் வியூவரா?
நல்லா வருது.
ஜூம் இங்க இருக்கிற சிஸ்டத்துல இன்ஸ்டால் பண்ண விட மாட்டாங்கடா. ஓகேவா? ஸோ இப்போ ஓகேவாடா? வாய்ஸ் கேக்குதா?
வாய்ஸ் கேக்குது.
ஓகே குட். ஸோ ஸ்க்ரீன் ஷேர் பண்ணுறேன். ஏதாவது எரர் வந்ததுன்னா சொல்லுங்கள். Okay. So once we set at that pressure field, and the next thing we're going to do here is we'll move on to that boundary condition. Okay, so I'll just in this boundary condition, just click on that operating condition. So in operating condition, make sure I'll have the value of 0.11325, that is the pressure value of the overall region, like that air pressure. So it's a default value. And then go to the solution. In solution method, I'll leave to coupled one and change the gradient method to that. Okay, so it's also been the same thing. Maybe we can modify the turbulent viscosity to the second order wind up for better accuracy, and also make sure it should be in that turned on, that pseudo transient mode. So once everything is get setted and click on solution control. Yep, so here we have the control option, double tap on it, and in this we need to change some values, that is modified turbulent viscosity, that is 0.75 to 0.9. okay, the energy is as it is 0.75, so I don't want to change that energy at all. Okay, once it is set it down, we'll move on to that initialization condition, and right now it is hybridized initialization. Click on initialize. Okay, we actually missed some of the values. What is that? Okay, we'll set everything in that boundary condition. So before that, once again, so click on monitor, that residual, make sure as everything is get started and in method is coupled. Okay, fine. Okay, so there is no option to define that density. Okay, density, that is 0.5. Okay, body force is 1 and modified turbulent flow is 0.9. Energy is 0.5. Okay, fine. Initialization, hybridized initialization, initialize. Okay. Warning. Condition only can be okay, ideal gas condition, fine. So that just go to see just only one values. So if you change one thing, so your problem will never converge. So just double tap on the boundary condition and choose pressure for and say edit. Here okay. So once again, close materials, air. I'll change the density to ideal gas condition and click on change and close. Okay, so you have to change the air as an ideal gas condition for this analysis. And initialization, now click on initialize. Okay, so now you get the values. So if you are getting the values like this, probably there will be a problem in your model, so you need to make sure everything will be correctly assigned or not. Okay, so once that value is initialized, so the next thing is you need to set the reference values. So for the future calculations, so how can I set the reference values? So here you'll have an option to set the reference values. So just double tap on it, and I will change the temperature to 0. So I want to compute from this region. So I'll choose the pressure far field 1 and change the condition to 0 and another values. So enthalpy use also 0. So you know that condition, what is enthalpy and entropy, and viscosity is 1. So the heat specific ratio is 1.4. I'll leave everything as it is. So I just change the value from 1.22 and 25. So you don't need to change the reference zone. So once you set it down that reference values, just click on that run calculation. Set the initial iteration parameters as a 50 and click on calculate. Now it is get initiated. Okay, but the calculation is completed, but it's not converged. Okay, so now what I'm gonna do here is I just create some parameters on the contours. So you can also view the result from here itself. You don't need to change, you don't need to close the entire thing and go for CFD post. So CFD post is only for the advanced result viewing process. For a simple results like a pressure variation and pressure drop in this model, you can also view from here itself. See, there is an option to view the results, result tab. So in result tab, in graphics area, just expand this. You'll have an option that mesh, contours, vectors and path lines like that. So just click on contours, right click and say new. So in this I want to view the pressure. So if you want to change this name like contour 1 to pressure, you can. So once it is settled, I want to view the pressure, that is static pressure. So at the region of either you can choose this wall or else I will just leave this. I want to draw the mesh factor also and say edges, display and close, save and display. Okay, close. So now you don't view any changes, but if I slightly zoomed in, you may view the results. Okay, so since it's a transonic flow, you'll get a maximum pressure at this region and minimum pressure at this region. At a blue color indicates there is a minimum pressure. That means we have a lot of velocity over here. So if you want to change that velocity to the condition, you can also view that velocity. Just click on this, double tap on it, change the parameter from pressure to velocity and say compute and click on save and display. See, and pressure and velocity is quite opposite to each other. So when the air is heated on this region, you may get a low velocity over here and high velocity right over here. So how can I say that it's low and high? So by using this chart, like this blue color indicates a minimum value and then red color indicates the maximum value. It's around 4.48 e power 02. Okay, and also you'll have that. So since this will occurs due to the poor element quality over here, otherwise the flow is very clear. Still this results is not a reliable one because we don't have any convergencies over there. So if you get the convergence results, then only the result will be much more accurate. Okay, so once you view this result, and the next thing we're gonna do here is I need to view some other results, that is node values. Just click on the plot. I already said in the earlier of the class, that is you need to calculate the wall y plus factor. So it's like a graph. Maybe you will get a graph like this. What it indicates is the quality of the elements which is around this wall. You have to get that value which is less than 1. So otherwise, if it crosses the value over than 1, so there won't be a proper mesh over this region. So that means this result is completely out of time. You need to change the mesh. So that y plus factor is completely depends upon the Reynolds number. So you know that Reynolds number, that is density velocity into ρ. So it's a ratio between the inertial force to the viscous force. Inertial force to the viscous force.
சார் இப்போ வேக்கோட இதெல்லாம் வராதா சார்?
புரியல, எதோடது?
வேக்
வேக்
என்னன்னா பிளேட் இருக்குல்ல சார்,
ஓகே.
அந்த பிளேட்ல இருந்து முடிஞ்ச பிறகு அந்த சொல்லுவாங்கல்ல, அது வந்து ஒரு சர்க்குலரா எடின்னு சொல்லுவாங்க.
ஓகே.
அது என்ன ஒரு வெர்டெக்ஸ் ஃபார்மேஷன். அந்த வெர்டெக்ஸ் ஃபார்மேஷனோட ப்ராக்ரஷன் வந்து எப்படி இருக்குன்றது தான்.
ஓ யா யூ கேன் லைக் அதோட வெக்டர் டைரக்ஷன்ஸ் எப்படி வந்துட்டு ட்ரான்ஸ்ஃபர் ஆயிருக்கு அப்படிங்கிறத பார்க்கணும் தானே? அதோட பாத் தானே, அந்த ஏர் வந்துட்டு எப்படி இதில் ஹிட் ஆகி போயிருக்கு அப்படின்னு சொல்லிட்டு பார்க்கலாம். Yeah, you can. So for that you will have an option called vector. Yes, in that just go to there and click on new. In this you can choose the location you want, so see later when we come to that particular point. Okay, so first we will complete that plotting of that wall y plus. So just click on the xy plot and say new. I'll choose the function as a turbulence and modify the factor, that is wall y plus, and click on close. Okay. Okay, everything is fine. Close. I just change the factor to 200 iteration and click on calculate again. Okay, so the problem is actually converged at 168, the solution. Okay, so to view the vector results, so as he asked, so what I'm going to do here is just go to vector. I'll use that scale factor as 15 and say save and display. So actually it shows the direction, but the arrow is too large. Maybe the factor is even small.
And the last
yes, we'll get this. See? So only why the way you get the arrow on the top side is because I just choose the wall top. Okay, so if I choose wall bottom also, you'll get the arrow at the bottom also. See, now you can view how the arrows gets insulated. So instead of if I choose this also, maybe okay, this is the flow of the air around this, right? So idana ketta
sir, நான் பவுண்டரியில கேட்கல சார், அதோட ப்ராக்ரஷன் இருக்குல்ல சார்.
ஓகே, எதோட ப்ராக்ரஷன்?
அங்க வர வேக்ஸ், அந்த இப்போ அந்த டெயில் விண்ட் இருக்குல்ல சார்.
ஓகே,
உங்களோட அந்த இருக்குல்ல முடிஞ்ச பிறகு
ஓகே
அங்க எதுவுமே இருக்காது, அங்க ஒரு வெர்டெக்ஸ் ஃபார்ம் ஆகும் சரிங்களா?
இது கிட்ட ஒரு வேக்யூம் மாதிரி கிரியேட் ஆகும் அப்படிங்கறியா?
ஆமா சார்.
இந்த
அதோட ப்ராக்ரஸ்
see இங்க இருக்கிற ஏர் வந்துட்டு அகைன் இட் will bring backs. ஸோ இந்த ஏரோ வந்துட்டு ஹிட் ஆகுறது தெரியுதா? இங்க வெக்டர் திரும்புறது
லாக் சென்டர்ல. ஆமா சார்.
ஓகே, ஸோ இந்த ரீஜனில் இது வந்துட்டு இப்படி திரும்பும். ஸோ இன்னும் வந்துட்டு இதோட கலர் கான்டூர்ஸ் அண்ட் தென் இதோட ஸ்கேலிங்கை மாற்றுறதுக்கான இது வந்துட்டு இருக்குது. ஸோ அதில் வந்துட்டு பார்த்தோம்னா இன்னும் நமக்கு நல்லா கிளியராக தெரியும். மேபி ஆரோட ஸ்டைலை வந்துட்டு நார்மல் ஆரோஸ்ன்னு மாற்றிட்டு டிஸ்பிளேன்னு. ஓகே, ஸோ இட் வில் பி மச் பெட்டர். இப்போ தெரியுதா கொஞ்சம் கிளியரா? இது எப்படி வந்து ஹிட் ஆயிருக்கு, ஐ மீன் டெயில் கிட்ட வந்து ஹிட் ஆயிருக்கு.
வாய்ஸ் மட்டும் தான் வந்திருக்கு, ஆடியோ வர இது மேஜர்ல.
See, is everyone facing this issue?
இப்போ தெரியுது.
ஓகே. ஸோ இதில் வந்துட்டு ரொம்ப மைன்யூட்டாக கவனித்தோம் அப்படின்னா இந்த இடத்துலலாம் வந்துட்டு திருப்பி ஏர் வந்துட்டு இங்கேயே ஹிட் ஆகிறது தெரியும். இந்த பொசிஷன் ஒரு டர்புலன்ஸ் வந்துட்டு இந்த இடத்துல நடக்கிறது. நான் ஒரு 2 minutes அப்படியே மூவ் பண்ணாமல் வைக்கிறேன். தெரியுதா? Okay, fine. So in this exercise what we actually do is a transonic flow, match number, so everything we have defined in this model, and finally we verified that pressure difference and velocity difference on this airfoil structure, and also verify the vector direction and the flow of the air which is hit on this airfoil structure. Okay, so that is for we are looking for today. In our next session we will see in another example. Okay, and you will get this recorded session on YouTube. Anytime you can view that and practice yourself at your end. And I will also attach that MSH file on the description. You can download from that. Okay.